Hello, everyone. Thank you for joining us today on this webinar on improving the accuracy of remote sensing for tree biomass webinar. I know there has been a lot of anticipation on what gold standard is doing on the application of remote sensing, specifically in the forestry sector for the issuance of well, mostly GSV-ERs, but also for impact claims. So I am joined today by my colleague Karen Dyson from SIG. I will just give a brief introduction. I'm Giancarlo Raschio. I'm a senior manager on sustainable finance and innovation. So I'm leading the work on remote sensing, which is applied to both carbon credits and impact claims. And I would like Karen just give you a bit intro on herself and about SIG.
Hey everyone, my name is Karen Dyson. I work for SIG, Spatial Informatics Group. We're an environmental think tank. The part of SIG that I'm working in is the environmental mapping group, and we handle a lot of environmental mapping focused on remote sensing with regards to carbon credits and carbon more broadly, as well as things like biodiversity. It's great to see you all.
Thanks, Karen. So just a couple of points. This webinar is being recorded. We're going to be publishing the recording on our website. And please send us any questions that you have in the Q&A box, and we will be addressing the questions at the end of the presentation. So we're going to cover a bit of the basics on what is Earth observations, acknowledging that some of the participants might not be experts on the field. So we just want to make sure that everybody understands the foundations on what is Earth observation, accuracy, and why we conducted this work and why we're going to be doing a pilot phase. The main objective of the work we did with SIG was to understand how to assess accuracy of remote sensing estimates of tree biomass. So a lot of focus of the work is on the how or why do we need to assess accuracy and how to assess accuracy. We will also take you through a live demo of the protocol co-developed with SIG. Also, we will mention the next steps regarding how we intend to pilot the protocol and how the protocol hopefully will be then integrated as an gold standard for the global goals official tool and requirement. So I will then hand over to Karen to take us through the presentation.
Great, thank you so much. Yeah, so I just wanted to chat quickly about what is Earth observation. Next slide. And we'll just do a quick overview just to make sure everyone is on the same page. So Earth observation includes data collected using sensors, and these sensors can be mounted on satellite, aircraft, UAV, so unmanned aerial vehicles, as well as in situ. And we consider both active and passive sensors. Active sensors are ones that send out a signal and then listen for the return of that signal modified by the Earth's surface. And then passive sensors essentially are using the sun to send information and then listening for that information being bounced off the Earth's surface, so how the sunlight reflects. Next slide. And there's a couple of key data sets that are important for forestry-based gold standard products. So for our passive sensors, these are optical data. So this is data from the visible spectrum, including red, green, and blue, as well as infrared and ultraviolet light. And for our active sensors, this includes things like radar data, through synthetic aperture radar, SAR data, as well as optical data, so light detection and ranging data. This is more commonly known as LiDAR. Next slide, please. And these data sets differ in a couple of key ways. The first way is the extent of the data, and there's kind of three different dimensions that we think about. The first is spatial So you might have a data set that's very limited to your local forest, and then you might have one that covers the entire world. The second dimension is temporal. So you could have a data set that's one time versus covering 20 years worth of data. And the third dimension is spectral data. So, or the spectral dimension. And this could be, limited to just that visible spectrum versus, multispectral, including the infrared or other parts of the electromagnetic spectrum beyond what we can see. Next slide, please. The second key way that data sets are different is in their resolution. And again, we have those three dimensions. The spatial dimension, so you could have a resolution where each pixel represents 1 meter, or each pixel represents, say, 30 meters. And there's data sets that are even more coarse than that, so 100 meters or more. And just as a quick kind of visual demonstration of this, I've included two diagrams on this slide. So on the right, you can see just a quick diagram. So an example of that 30-meter pixel is that largest box. That's a Landsat pixel. And you can see how large it is in relationship to a fake tree that I've included for scale, right? That tree is about 10 meters by 15 meters. So it's a large canopy. But you can see how much larger that pixel is than the tree. And this is kind of a really key point. And for the protocol, which is why I'm spending a little bit more time here. On the converse, you can see the planet NICFI or the NAPE pixels, planet NICFI being about 4.7 meters, and the NAPE data about 1 meter. And you can see how many more of these pixels will actually fit inside of the tree instead of having multiple trees fit inside of one pixel. So resolution can also be temporal. There are some data sets that are collected every day. Some data sets are collected every 16 days. And then there are some that are collected on the scale of years or more. And then finally, the spectral dimension. So that's the width of the, for a visible or a electromagnetic spectrum. That's the width of the wavelength. So you could have one data set where all kind of blue is in one wavelength and one versus, where there are multiple different bands for each of the shades of blue. Next slide. So with that kind of quick background, why use Earth observation for carbon credits and impact claims? Next slide. Well, let's compare the traditional versus the Earth observation approach to measuring carbon. So the traditional approach is something I'm sure you're all familiar with. It involves ground-based field teams, visiting field plots, using equations to estimate carbon based on that field data, and you generally have repeated measurements over time. And the traditional approach is generally pretty complex. You need to take into account stratification, sampling, traveling to many sites, many of which can be in remote areas, establishing the measurement plots, measuring every tree by hand in the plot, cleaning the data, assessing the data. And the EO approach includes some of this. So a lot of them are hybrid with ground data and Earth observation data, although some are Earth observation data only. And basically, the main approach is develop models to estimate carbon based on combining these two sources of data. So it's really using Earth observation data to reduce field team time, as well as sometimes the repeated measurement frequency. Next slide. And this means that there's some advantages to the Earth observation approach. The first and main one is cost. So generally, because you're combining field collected data with that Earth observation data, either from satellite or UAV, or collected out in the field, you can generally do fewer plots, which means less field time, less resources, both in terms of money and in terms of personnel. And this generally means that smaller projects are more feasible. So there's more potential forest area that can be managed and conserved as as these smaller projects can be brought on board. And then kind of the third advantage is fast detection. So some EO approaches, particularly those that involve satellite data, have kind of automatic data collection, either on that, some of them are daily, some of them are essentially biweekly. And this means that you can get fast alerts to, for example, loss in forest cover. So there's essentially near real-time data in order to detect potential forest loss happening that you might not know about. So instead of having to wait until you go back out in the field and, unfortunately finding that there's a section of forest missing that you weren't expecting or some trees missing that you weren't expecting, there's a lot quicker feedback, or there can be a lot quicker feedback here. So next slide. I think we have a poll that the team has set up. I think that happens in the background. So unless we have those results already.
Yes. I can see now the poll. So please select your option and click submit. So the question is where we are currently using remote sensing to measure tree biomass. Mostly appears to be not yet, but planning to do so with 58% of respondents. 12 responses so far. Let's give it a couple of more seconds. If you haven't replied to the poll, please do so. It seems that, yes, 58% are not yet using remote sensing to estimate tree biomass, but are planning to do so, although there appears now to be more people saying yes, but definitely the majority is not yet using it for, I would assume, measurement and reporting of tree biomass. So I guess we can now close this poll and continue with the presentation. I'm sorry, Karen, you're on mute.
Apologies. Yeah, so that's really exciting. It's interesting to see how many people are already using Earth observation, as well as how many people are interested in it, which kind of underscores, why do we need to assess accuracy? So next slide. And this is really, the credit market depends on both credibility and trust in carbon credit accuracy, in order to underpin those values of the credits themselves. And a similar demand is really growing for impact claims. Next slide. And some of the EO data products that are available right now advertise a high accuracy globally, but we need to independently verify based on project-specific conditions and location. And this is because a model that's built in one forest condition or type may not be appropriate for different forest types or conditions. And a map that's built to handle multiple forest conditions across a region, or even sometimes globally, can miss local scale variability that's really important for, for carbon. So in general, it's best practice in all cases to explicitly test the map with independent observations in the location and time for which a map is made. Next slide. So this means that assessing Earth observation approaches for accuracy is really important. And these methods need to show that they reflect on the ground forest conditions, show that they're unbiased, that is, they don't consistently over or underestimate carbon, describe uncertainty, and that includes over or underestimation. So essentially, we need to know how close to, what's on the ground these maps are in order to be able to, help underpin that credibility and trust in the carbon credit accuracy. Next slide. So now I want to talk about how we can assess accuracy. Next slide. Yeah. So we have a couple of practical considerations. When assessing accuracy, we're really interested in maps that are being used to initialize carbon credits and maps that are being used to issue ongoing credits. And we have to assume that we don't have access to the proprietary model workings, right? Because a lot of these maps are, how they work is kind of proprietary business knowledge for the providers. So we have to assume that we can't see any of the inner workings. All we can see is kind of the resulting map. Next slide. So we use statistics. We can use a model-assisted methodology to evaluate uncertainty in these biomass or carbon maps. And these statistical models relate field plots to the vendor map output. And there's basically two pieces of data that are required. The first is biomass or carbon estimates from the field plots, and the second is your map output. And we go very much into detail in the theory of this in the document we released for public comment earlier this year, and you can find that on Gold Standard's website. Next slide. And we'll pause here for the second poll.
So the poll is: what barriers, concerns do you face in using remote sensing for estimating tree biomass? So you can select multiple options and submit. Let's see what we have. Wow, 60% so far is accuracy. Let's see if we get more responses. So it seems to be a bit of a tie between accuracy and data availability, with cost increasing a bit, but not getting near to accuracy and data availability as main barriers and concerns. We're going to give a couple more seconds for those who haven't responded to send their answers, but I think we're pretty much there. So it appears that the main concern or the main barrier for the use of remote sensing on estimating tree biomass is data availability with 44%, followed by accuracy with 39% and cost with 17%. Interesting. Thank you, Karen, over to you.
Thanks. Yeah, so when thinking about these things, we needed to design a protocol that essentially could assess accuracy given essentially those two things, right? Our maps and some source of field data. And next slide. There's a couple of important pieces of background information for kind of how we were thinking through this protocol. So the first is that all maps have error. And we also know that maps have more error and more bias when they're externally calibrated and when there's no field data collected. And what we mean by externally calibrated is essentially the model is made based on data, in this location, but then it's applied somewhere else. So it's calibrated and then applied to somewhere outside of that calibrated area. So there's a couple of specific EO data sources of error. that can go into this piece of maps have error, right? So the first is noise in the data itself. There's multiple sources of this, and it's actually, it's a whole field of study into itself. But some of them are, for example, there can be slight differences between where a pixel thinks it is and where it actually is, right? So the registration for the pixel can be slightly off from its real world, like on the ground location. And there can also be some, noise in the, in the returns just from the sensor. There's, lots of potential issues there. And then the second is model uncertainty for estimating the parameters. So this is uncertainty from the model itself. So when the vendor is developing the model and coming up with the estimates, the map estimates, that, those are kind of the two key sources, So essentially it's error from the data itself, and then error from how we're calculating the biomass based on that data. So, both of, like I said, both of these sources of error, the further away the verification data is collected from the project, the higher discounting should be applied. So that's kind of, that last piece is kind of taking into account everything, that we know about these sources of error, that we know about how bias increases when when maps are externally calibrated, and then coming up with kind of this idea that the more, that uncertainty should be kind of tied to discounting. So next slide. So we have two data requirements for the protocol, and these are fairly loose in order to have an initial kind of flexible situation. The first is that Earth observation-based biomass or carbon map, and the second is field data. So the minimum here is 30, and these should be randomly selected using probability sampling. So next slide. And it's this field data type that we've built some flexibility into, and that determines the uncertainty detection. So for this initial kind of design of the protocol, we included 5 different field data type classifications. The first is field data from the project area. So that's, your carbon project is in a location, all your field data is from that location. That's kind of the highest quality. The second is field data from adjacent similar reference sites. The third is field data from similar reference sites and similar ecosystems within the same ecoregion. The fourth type gets a little further away, and this is field data from similar reference sites and similar ecosystems, but they're outside the ecoregion. And that last type of data is really no plot data, so only Earth observation data is used. And just a quick note here, that by similarity, we mean it's similar in terms of, biological factors like tree species and stand mix, as well as abiotic factors like elevation. Next slide. So based on this data, we can identify the methods used, and we use the data type for this to kind of determine how the project can flow through this protocol. So for this, type A or B data goes to scenario 1. Type C or D data goes to scenario 2, and no data goes to scenario 3. And these are all kind of based on different kind of discounting levels based on the uncertainty. So a quick note is that all users or the idea is that all users will need to migrate to type A data for the recalibration and revalidation steps. There's also an important point here in that we need to identify if field data was dropped, and if so, why. By dropped, I mean, was a data point removed from analysis? Was there a field data point collected that wasn't included? So dropping field data during validation is generally not allowed. Plots are important information for assessing the model fit and appropriateness. And really, we should only be dropping plots when there's a clear measurement or data entry error. So for example, we know it's mature forest and the average DBH is 5 inches, so tiny trees. So obviously maybe that should be 50 and it was a data entry error. Or there were clear differences between the plot and the project area. So perhaps the plot was taken in a wetland and the project area is more upland forest. And just to give you a quick example, in a space you might be more familiar with, say there are 5 data points for test scores in school, and one is lower than the others. And you drop that one from the calculation so that your average for the class is higher. In the same way that if you ignore a bad test result, you can have a higher average in class. If you drop a data point that doesn't make your model look good, it can improve the model fit. So when field data is dropped kind of outside of these clear data entry or error pieces, we would need to assess kind of a maximum penalty. Next slide. So now let's chat about the protocol application. So we developed for the public comment easy to use Excel spreadsheet, and this is the R Shiny application. We then kind of took that Excel spreadsheet and took away a lot of the challenge in terms of having to run your own regression to calculate the model assisted error. So this does it all in the back end. Next slide. Sorry, I guess next slide. Apologies. And just a couple of quick notes. This is not being used for current projects. All values are placeholders. So all the values will be modified. The discount is a safety discount that's based on the type of data. And this is on top of the gold standard compliance buffer. And the deductions and issuance approach that's based on Earth observation approaches will be defined after the pilot phase for this protocol. And more information on the pilot for the protocol will come later.
Yeah, just a note to let you know that later on we will show an example on what we mean by these safety discounts, and as Karen mentioned, is not something that is already defined. It's just an approach, and the actual values will be defined after the pilot phase during the official review and approval process of this protocol by Gold Standard. Yeah.
So just a quick note that this is currently being worked on, and this is something that might be used, but it's not post, is still pre-pilot.
So I will share, let me stop sharing here. I want to share the protocol with you. Just one quick second. Okay, so let me share the screen. Please let me know if you can see it. And you see the protocol?
Yep.
Oh, sorry. Okay, perfect. Let me see if I can make it bigger. Okay.
Yeah, that's perfect. Fantastic. Yeah, so I'm just going to walk through a quick live demo. And this is an example scenario. Our test data or our pretend data is from a forestry project. We're using an Earth observation-based biomass model. We have 30 plots of type A data, and there are 800 map pixels for our study area. So the first thing you'll see is the welcome screen, and then the next screen is, oh, you're good, is to select the data type. So here we have type A data. So let's select type A data. Perfect. And now we can hit next. And then we can hit the browse button. And then you'll be able to click on a file. I think it just shows the web screen. So there'll be a pop-up here that shows your different things, but how screen sharing works with Teams, you can't actually see the pop-up. So you click on your input plots, your plot data, and then you upload your map pixel data. And once both of these are uploaded, you'll see this screen, which allows you to verify your inputs. So we can see that the number of plots is 30, the number of map pixels is 800, so that's what we expected. And then we can see the data for the map pixels and the plots there. And that's what we expected to see. So we can hit next now. And this automatically calculates all of that information that we were talking about. And the discount rate here is that, like I said, that safety discount. It's based on the type of data that's used, and this will be on top of the gold standard compliance buffer. All the values are placeholders. They're just places to start and will be verified after the pilot or during the pilot. So here you can see that there's kind of carbon estimates. You can see the test discount rate, lower and upper ranges, as well as standard errors and upper and lower limits on the confidence interval. So the application also has some data entry and errors that it provides if you provide it with the wrong data. So if here, for example, we have only one plot in our plot data, so there should be a file called input one plot. Yeah, it'll give us an error. It says too few plots. And here again, you can see that in the summary of the input data, we can see the number of plots is 1 instead of that 30 that we were expecting. As another example, if we switch back to the normal plot data, and then if we have values that are kind of outside of what we would normally expect to see, so there should be a file for the map pixel data for invalid data. Yeah, and then we see that it'll give us an error if we have negative numbers, or if we have numbers that are higher than any values currently known on Earth. And the here also this file actually has 2 errors. We can also see that there's only 3 map pixels, which is not what we would expect to see. There should be at least the same number of map pixels as plots, and usually there are many, many more map pixels than there are plots. So that concludes the live demo. It's a very simple interface meant to make your life easy. And I believe we're going to talk about an example of the petition.
Let me quickly go back to the presentation mode. So please let me know if you can see my screen. Can you see the presentation? Good. So, well, this is the example that was used in the live demo. And okay, wait just 1 second. Okay, so Based on the expected safety deduction that Karen mentioned, as you also noted, that is something that might take place on top of the regular 20% buffer deduction already applied by gold standard. So what we mean by the safety deduction is not a deduction in the true sense, but more of a withholding of the issuances based on the accuracy of remote sensing estimates. So for example, if our growth model gives us a result of 100 VERs per year, usually what happens is that a project has to conduct a forest inventory, and only based on the results of a forest inventory is the project can issue the accumulated number of VERs, let's say for a 5-year period. With the application of remote sensing, what we are trying to do is to, based on the accuracy of remote sensing, allow for annual issuances with certain withholding, which is this safety deduction. For example, if we have 100 VERs per year estimated issuance, and the accuracy of our remote sensing prediction has been established at 70%, what we see here is that the issuance will be 70 VERs based on remote sensing estimate, and 30 VER would be withhold. And those would be withhold in years, let's say 1 through 4. And then in year 5, projects will have to conduct a forest inventory to verify the accuracy of the remote sensing model, but also to recalibrate and revalidate the model for the next, let's say, 5-year period. Now, the length of the period, again, is still to be determined based on the results of the pilot phase. But what we expect to happen is that, assuming that the remote sensing model was confirmed to have 100% accuracy, on year 5, the issuance will be 70 VERs plus 150 VERs, which are the 120 VERs that were withheld between year 1 and 4, plus the 30 that were not withheld on year 5 because the expected accuracy was achieved. So again, the safety deductions are still to be determined. This approach is our first iteration on how to apply remote sensing estimates. This is not an approved yet approach by gold standard. The actual approval and the final version of this will depend on the results of our pilot phase and on the results of the official review and approval process that will take place after the pilot phase. So the pilot will start next year. We can think of the pilot in 2 phases. The first phase is for us to collect tree biomass data in divergent geographies. It could be either that it's primary data, meaning we go to the field and collect data, and or secondary data, meaning data that is provided by gold standard projects, let's say forest inventories, and the data is validated as part of the pilot phase. So in essence, it would be something similar to what happens with a VVB when the VVB checks the accuracy of a forest inventory. We will use that data to test our protocol to see how it works with actual data from like on-the-ground data and EO maps. We will revise and update the protocol, which will then be submitted, as I mentioned, for an official review and approval process by gold standard. And as a result, we will have 2 things: the final protocol to be used and what we call sort of like data packages to test the accuracy of proprietary algorithms or vendor algorithms. The idea is something like this. Imagine we have data points from 10 different plots in different geographies. So we draw randomly 3 of those data sets and develop one package. So that package is then provided to assess the accuracy of a vendor. So for example, I could tell a vendor, assess how much biomass was in the year 2024 for these 3 plots. So the vendor will provide the estimation for the 3 plots. We will have the actual measured amount of biomass, and we can then plug in those 2 data sets as we did in the live demo, and the tool will assess the accuracy and the scan for us. Now that will happen in phase 2. For phase 1, we expect to start that next year Q1 and complete the work in Q2 2026, meaning have the protocol approved by gold standard, assuming we find the protocol works as expected, or have the changes necessary, but already have the protocol gone through the review and approval process, have the data packages, and that will take us to phase 2, which is the actual application, still in a road testing phase. We will call for, we will release an open call for testing the accuracy. We will invite vendors, technology providers to assess the accuracy of their algorithms or proprietary algorithms. We will have a testing period. We'll collect the results, assess the results, and what we expect is to release a list of vendors whose algorithms are above a certain threshold. And ideally, what we expect is at some point to have the option, or to provide the option for users to either go for the regular approach, which is issuance only based on forest inventories, or to go for this hybrid approach, which is the use of remote sensing estimates with periodic recalibrations, revalidations based on forest inventories. And we will provide a list of vendors that are above a minimum threshold of accuracy. We expect to have to test this on GS certified projects and to start doing the testing between 2026 Q4 and 2027 Q4. So it's 1 year of testing this on actual projects to understand also issues and risks that may arise based on the issuance on just remote sensing estimate with periodic recalibration and revalidation. So please stay tuned for updates on this pilot phase. Again, we welcome projects that are interested in providing their data, in collaborating with us. We are still defining, fine-tuning the details of how we want to engage with existing projects, to collect data, to use their data, to validate their data. And we will be posting more information on our website on the exact timeline and steps that will follow. So now I would like to open the floor for questions. Let me see quickly. Just let me stop sharing because I cannot see. There you go. So we have one question from Hugo Troll. Sorry if I'm mispronouncing it. So the question is an EO-based biomass map above ground biomass product, for example, mandatory to calculate the accuracy? Or do we have the possibility to use vegetation index or other proxy of biomass amount? So Karen, I guess in essence, the question is whether we need, or the user needs to develop an EO-based map, or is it possible to just estimate biomass by using vegetation indexes or other proxies of the biomass amount?
Yeah, this is interesting. I think you can see more questions than I can. Yeah, so essentially all of those are EO-based biomass maps. The thing that I will say is that, remember when I was talking about kind of that model and how different models can have different errors. We do know that there are some approaches to estimating biomass using EO data that are more accurate than others. And that varies a little bit around the world based on the qualities um, of the trees themselves. But technically, those are all EO maps. But I would expect some of them to be, some of the more simple approaches, just using, a greenness index, is going to be a lot less accurate than things that are kind of taking into account multiple different descriptions of trees. I think is the best way I can answer that.
Thanks, Karen. So there are two questions that are kind of similar and refer to whether it is already allowed to use remote sensing for the carbon stock quantification under gold standard. So let me confirm to all of you, this is not yet allowed. The only eligible approach at the moment to issue carbon credits from forestry projects under gold standard is to conduct a forest inventory, and only then carbon credits can be issued. So for remote sensing to be allowed, we need to complete phase 2 of this piloting phase, meaning at the end of 2027, we will have all necessary data to be submitted to gold standard to make a decision on the actual approaches of the protocol, the safety discounts, and most importantly, I would say any additional safeguards and the final approach of whether we're going to have with annual withholdings or any other approach. So the idea is to provide some safety for the project developers that are issuing VERs based on remote sensing, in case there is a reversal event or a low performance event. So think about what we already have under gold standard, the plan emission reductions or PERs for forestry projects. So these are ex-ante units. Sometimes there are underperformance or reversals, and there for those scenarios we have rules for the performance shortfall under the performance shortfall guidelines. If at some point gold standard allows the issuance of VER, so now we're talking about ex post units based on remote sensing, and there is a performance shortfall event or reversal, the situation is way more serious. Therefore, we need to make sure that we are managing the risks correctly and that we have all the safeguards needed in place. So again, just to confirm, we are not allowing the use of remote sensing or EO biomass estimates at the moment until we complete phase 2 of the pilot phase. And that also relates, I guess, to the question from Kasia Tokarska on reversals. We will need to revise our performance shortfall guidelines to account for the issuance of exposed units based on remote sensing estimates. Then we have another question from Janardan Roy. It says, for a multi-species model, does the model require 30 data points in total, or we need 30 data points for each species like mango, lemon, etc.?
Yeah. So this is a good question. And just thinking kind of more broadly, if your project area includes different forest types, stratification is always helpful in terms of identifying accuracy. And this is definitely something that I think the pilot will get more detail on. Before we've undertaken that pilot, the current minimum is 30 field data points total, but more is always better. That's really just kind of a lower guideline.
So we have a question from Daniel Prieto. It says, it has been presented a number of 30 plots to assess accuracy, but what is the minimum or maximum area to get a number of plots? Is there any rate? Example, 1 plot per hectare?
Yeah, that hasn't been defined yet. And I think this is definitely something that the pilot will help address. Obviously, you can think of very small projects on the smaller end where trying to get a lot of different plots would be difficult. One thing, and I think there's another question about the minimum plot size needed. And these two actually kind of tie together. From a statistical perspective, the easiest way to do it is so that your plot size and your pixel size are the same. And that actually generally has a smaller pixel size, a smaller plot size than some are traditionally. And within your project area, if it's possible to get 30 plots, that is definitely the recommended. Otherwise, going to adjacent sites would be that type B data. And that's definitely something that I think will be better pinned down in the pilot. Hopefully that.
Okay. So there is another question also from Daniel Piero, whether there are any requirements to participate in a carbon project during the pilot phase that was presented before. So I understand that you mean projects that have been registered, whether they can be part of the pilot phase. So definitely yes. The exact requirements, we are still working on those, but I think the key one will be for projects to have available data from forest inventories, or planning to develop forest inventories during the time where this pilot phase will be taking place. So if a project has data from a forest inventory and is willing to share that data, we will have, of course, rules in place to be sure that the data is managed properly, and also we will need to do field work to validate the results of that data. Think about what happens with a VBB during a verification where the VBB established sampling plots to just check on the biomass estimates and the accuracy. So then there is a question from Janardan Roy. What would be a good feature to differentiate biomass of two species having similar canopy from optical remote sensing perspective? For example, a 4-year-old guava and 7-year-old mango.
Yeah, so this is kind of a more technical question that's a little bit outside of the scope, but just quickly in case other people have similar questions. Yeah, so this is one of the challenges, particularly with using only optical remote sensing, is that things from from satellite imagery or from aircraft optical imagery can look pretty similar, even though they have different biomasses. So this is generally where you get into kind of one of a couple different approaches. You can add more spectral information. You can add some of those active data sensors, like we were talking about, particularly LiDAR or SAR, and that can help provide more information about the volume of the canopy. And then the there are also some data processing pieces that are sometimes helpful, including calculating things like rugosity. So differences in texture can sometimes be indicative of different canopy volumes, despite looking similar. That said, something that's 4 years old and something that's 7 years old, there's not going to be a huge amount of it can be very challenging, I'll say, to discern differences in the absolute biomass, simply because estimates of biomass using EO data, the errors can be larger than a single growth year or even multiple growth years. So, very, very brief answer, but hopefully that helps.
So we are almost at the end of the hour, so I guess we can answer one last question. So this one is, if an EO map is generated using a set of field data points, can the same set be used as part of the protocol for assessing accuracy?
Yeah, so this is a really good question. Best practice is that your training data and your validation data are different. And frequently what's done is you'll collect a bunch of field data points, and then to train your EO model, you will use a certain portion of those plots and reserve some for the validation. And that's current best practice. Using the same set of plots for both is going to overestimate your accuracy of your map.
Okay. So we are at the end of the webinar. I want to thank you all for joining us today. Thank you, Karen, very much for the presentation. And as we mentioned, this webinar is being recorded, will be available on our website, and please stay tuned on the next steps, also by joining our newsletter and the QR codes that are available in the presentation. And again, we will start this pilot phase work earlier next year. And yes, it's exciting to start exploring the applications of remote sensing. I know there is quite a lot of interest and a lot of also uncertainties around the application of this. So again, thank you all for joining us today. Have a good rest of your day. Bye.